Today we're going to continue our discussion on perception. So this will be perception part 3, and then we will be moving into talking about attention. Before we start the lecture, let's do a demonstration. What I would like for you to do is put down your pen or pencil and reach for something nearby. After you do this, reflect on the processes required to do that task. So, how did you do that task? How is it that we can use perception to navigate through our environment? How do we use perception to perceive motion? And how are perception and action related? These are all questions that we'll address in today's lecture. Vision researchers think that we have two visual systems that play a role in how we navigate the world. The what system helps us identify objects from perceptual information, and this is a conscious process. The what system is also referred to as the ventral stream, where the information projects to the temporal lobe. The ventral stream is considered vision for perception, given that the primary role is to construct a right and detailed visual representation of the world so that we can identify objects and events that we can attach meaning and significance to. The where or how system helps us identify where an object is located and how to interact with that object. This is an unconscious process. We also refer to this system as the dorsal stream, given that information projects to the parietal lobe. The dorsal, or where stream, is responsible for vision for skilled action, such that this stream engages in accurate moment-to-moment computations in order for us to move relative to our world. When you were asked to reach for an object, the what pathway allowed you to identify what object you needed, and the where pathway allowed you to locate that object and reach for it in space. In 1982, Ungerleider and Mishkin conducted an animal experiment that demonstrated evidence for the what and how system dichotomy. In this object discrimination experiment, they gave monkeys tests emphasizing either an object, which would correspond to the what pathway, or a location, which would correspond to the where pathway. For the object discrimination task shown here in image A, the monkey was shown an object, specifically the square cube that's on the right, and had to identify the object on the board. Once they completed the task, they received food, which was hidden underneath the object. The what pathway, or the ventral stream, plays a role in the monkey's ability to identify the object on the board. The location discrimination task, shown here in image B, required that the monkey determine the location of the object. They had to figure out which shapes on the board had the food underneath it. They were trained that the object closest to the cylindrical landmark was where the food would be. This task implicated the where pathway, or the dorsal stream. After the monkeys were trained on these tasks, the researchers cut out a small part of the monkey's brain in either the parietal lobe or the temporal lobe. Given what you know about the what and where pathways, what do you think happened to the monkey's performance who had temporal lobe damage? What about the monkey who had parietal lobe damage? What they found out was that monkeys who had lesions in the temporal lobe could still do the where task. That is, they could still locate the object closest to the landmark because this task required the dorsal stream. However, they could no longer do the what task. They could not identify the square on the board in order to find the food due to damage to their what pathway. Monkeys with lesions in the parietal lobe could still do the what task. They could still identify the object on the board with the food because this task required the ventral stream. However, they could no longer locate the landmark in order to select the item closest to the food due to damage to their where pathway. This research provides some evidence that there are two systems located in distinct parts of the brain that play a role in our ability to function in our environment, but they do play a role in a different way. One system allows us to interact with the world, such as grasping for an object or locating an object, while the other system allows us to identify objects. Another key takeaway from this research is that if one of these systems is impaired, we still have the ability to function in our environment through the other system. Another study conducted by Milner and Goodale in 1995 provided human evidence for these two pathways. Following carbon monoxide poisoning, patient DF had damage to her temporal lobe. The case study with DF demonstrated that damage to the ventral stream resulted in the inability to identify or recognize the size, shape, and orientation of visual objects. However, she had an accurate ability to guide her hand and finger movements. Using a perceptual task and a visual motor task, researchers were able to show evidence for an impaired what pathway and a functioning where-how pathway. In one task, DF and control patients were asked to orient a card to match the orientation that they were presented with. As you can see in the two circles at the top of this image, DF's ability to match the perceptual orientation was significantly worse than the control patient's. She's just kind of all over the place. DF was not able to perceive the orientation of the object and the environment well enough to match the orientation of her hand to the target. In the other task, DF and control patients were asked to put a letter into a slot. In this visual motor task, DF demonstrated similar performance to that of the control patients. DF's results are the same as the control patients, suggesting that she was able to complete the task when an action was involved. When she was unable to identify the object, she still maintained the ability to grasp and use the object for their intended purpose. So, how accurate are these two pathways? We know that we have a what pathway that allows us to identify objects, and a where pathway that allows us to locate objects. So is it possible to trick these systems? Are both these pathways susceptible to illusions? Take this image for an example. Look at both of the center circles. Which circle is bigger, the one on the right or the one on the left? They're actually identical in size. This illusion is referred to as the Ebbinghaus illusion. So why is it that you saw the circle on the right as larger than the circle on the left? What kind of processes are at play here? Research by Hoffenden and Goodale in 1998 sheds light on why we are susceptible to this illusion. They created a version of the Ebbinghaus illusion that we just demonstrated using actual objects. Specifically, they used poker chips. Participants completed a manual estimation task where they had to show the size of the inner chip using their thumb and index finger, similar to what you see in this picture on the right. These participants judged the inner chip with smaller circles surrounding it to be larger than the inner chip with larger circles surrounding it. However, the centers of those circles were exactly the same size, just as in the demonstration we completed. However, when they were asked to pick up the center chip during a grasping task, subjects used the same size grip for both chips. The illusion didn't hold when grasping for an object. The vision for action stream, remember that's the where-how pathway, was seemingly unaffected by this illusion. So what does this suggest? Which pathway can we trick, the what or the where pathway? That's right, we can trick the what pathway. One explanation for why we could trick the what pathway is that perception typically involves relative, not absolute judgments. The relationship between objects and a visual display play an important role in scene interpretation. Misjudging size and distance has far less of an impact than miscalculations in the visual motor domain, which could be problematic when it comes to navigation. Another implication of these examples is that shape processing of information is different for these two streams. The ventral stream processes information holistically, whereas the dorsal stream processes information computationally. So even though we perceptually see these objects as being different in size, we can still accurately reach out and grab those objects Furthermore, these experiments demonstrate converging evidence for two separate visual systems: a conscious system for object identification and an unconscious system for the location of and working with objects. As we just demonstrated, research shows that our perception of the environment can be inaccurate and susceptible to illusions. So, what if I were to ask you what the steepest hill you've ever climbed has been? Like most people, you'd probably overestimate the steepness that you experienced. But if we are biased to overestimate steepness, then how is it that we can accurately climb up stairs? We know from our previous examples that our unconscious how system engages in accurate moment-to-moment computations in order for us to move relative to the world. The dorsal stream is egocentric. The frame of reference is relative to ourselves and the environment. The system deals with the absolute size of objects with respect to the person. In contrast, the what pathway, remember that's the vision for perception or the ventral stream, uses scene-based frame of reference, which encodes size, orientation, and location of objects relative to each other. Research by Prophet et al. In 1995 had people rate the steepness of hills. What they found was that subjects overestimated the steepness. However, when they placed their palms on a flat board mounted on a tripod, people made almost perfect judgments. The flat board allowed them to engage in an ego frame of reference relative to the scene frame of reference to make their judgments. In summary, converging evidence suggests that we have these two separate visual systems. We have an unconscious system for object identification that is subject to top-down influences. Remember, that's our expectations and knowledge of the world that can influence our perception of objects. And we also have an unconscious system for the location of objects and working with objects. While the conscious system can be subject to biases and illusions, the unconscious system maintains its accuracy. And both of these systems together help us navigate throughout the world. Motion helps us perceive information and serves a few key functions and is important for several reasons. For example, motion perception provides information about objects in our environment. Consider camouflaged animals, which have the same color, shape, and pattern of their surrounding environment. Without motion, these animals would go undetected. The movement of the animal perceptually organizes all of these elements based on the common fate principle and reveals a figure that is separated from its background. Furthermore, by moving around a stationary object, we as the observer can see different perspectives of the object, which provides us more information about the characteristics of that object that are not obvious from a stationary perspective. Another important role of motion is that it attracts attention. Movement of something can result in directing your attention to the object. For example, if you enter a party and you try to find your friend among a huge crowd of people, it helps if your friend starts to wave their arms back and forth to capture your attention. It's through this attentional capture that our attention is automatically drawn to salient objects in our environment. And lastly, motion perception provides information about the environment. As you navigate through your day, you encounter many objects in your environment that are moving and provide information about the context of those situations. For example, if you walk past a crowd of people talking, you can get a sense of the intensity of the conversation based on their gestures. In one study, conducted by Heider and Simmel in 1944, they had participants look at an animated film, kind of like the one that you see on the right. And the objects appeared to move in various ways, going into the house and sometimes interacting with each other. The nature of the movements led participants to make up these stories to describe these objects as having feelings, motivations, and personalities. So here we see how motion of the objects conveyed information beyond the basic size, color, or shape of those objects. It actually conveyed information that was implied through the movement. Life without motion due to disease or trauma can result in the inability to perceive and understand movement. This is referred to as motion blindness. A patient known as LM was unable to perceive motion after having a stroke. This resulted in the inability to do basic tasks like pouring a cup of coffee, which she described as looking like something had been frozen, like a glacier. So we can see that motion plays an important role in our ability to interact with the environment. So our perception of motion allows us to engage in action. So what are some of the stimulus conditions for the perception of motion? For real motion, if an object is moving, you experience the perception of motion. But there's this other special case referred to as illusory motion. Other stimulus conditions result in the movement of an object when the target is actually not moving. So even though the target is stationary, we see them as moving. Today I'll talk about two types of illusory motion, specifically apparent motion and induced motion, and I'll provide examples of both. The first example of the motion illusions is called apparent motion. In this example of motion, an object appears in one location at time 1, another location at time 2, and another location at time 3, and this just repeats, kind of like how the next slides will look. Here is the actual stimulus, but the perception is that you have a single object that moves back and forth. Even if you make the objects distinct, like changing the colors, you'll still perceive the motion. But all that is actually there is a dot and a rectangle. Apparent motion is why you see the motion on LED advertisements like the image here on the right. All that is happening is that the lights are coming on and off. Similarly, when you watch a movie, lights on your TV are turning on and off, but we have this perception of motion. Induced motion is the second type of motion that I wanted to talk about today. Induced motion occurs when one object, usually the larger one, causes a nearby stationary object that is smaller appear to be moving. The background is moving, but you perceive the target to be moving. For example, the moon usually appears stationary in the sky. However, if the clouds are moving past the moon very quickly, the moon can appear to be racing through the clouds. The movement of the larger object, in this case the clouds, make the smaller object, the moon, appear to be moving. Another example occurs regularly, maybe, if you drive. So when a truck in the lane next to you starts moving while you're stopped at a stoplight, you perceive yourself as moving and may become disoriented for a moment. But what is really moving is the background scene, not you. The larger object is the thing that's moving. The interesting thing is that we have a lot of information telling us we are not moving. We have our vestibular sense, for example, telling us our balance system and that we're not moving in space. But the visual system has a powerful influence over what you experience perceptually. A classic demonstration of induced motion is the swinging room illusion. So in the swinging room demonstration, you are standing on a static floor and the walls and ceiling are designed so that you move back and forth, making you feel as though you're moving forward and backwards, even though you're stationary. If you watch videos of this, you'll see kids falling over, but typically adults won't fall over. They'll just move forward or backwards. The moving walls create a sense of self-motion through optic flow, which is the pattern of changes on the retina as you move through space. And this brings us to our next topic, action-specific perception. Our perception of the world follows from our ability to act on the world. How is it that perception and action are related to each other? And how does motion help us perceive information? Perception itself does not operate independently of action. Perception is interconnected with motor processes that turn information into movements. And so far, we've been focusing on the division of labor between the dorsal stream and the ventral stream. But it's important to point out that these two streams do not work in isolation with one another. They are not as localized or modular as presented. Rather, they are distributed in that they work in parallel, allowing us to process object information so that we can act on these objects in real time. The simultaneous activation of these two streams leads to a visual perceptual experience during the performance of some skilled action. Tools are a great example of this. You need to know what a tool is, you need to know what that object is, and how to grasp that tool so that you can use it for its intended purpose. For example, if you see a hammer laying on the table, you need to be able to identify that object as a hammer and know how to properly hold that hammer in order to use it to nail something into the wall. Research agrees that vision serves action, but the way that vision serves action is up for debate. One extreme proposes that we see things for exactly what they are. You see a ball and you know exactly the diameter of the ball, or you see a desk over in the corner and you know exactly how far that desk is away from you. On the other extreme is the concept of affordances developed by Gibson. An affordance provides one example of how perception and action are linked. Affordances are the actions that can be done on objects. For example, a chair can be used to sit on, you can use it to stand on, to extend your reach to grab a book, or you can use it to hold a door shut. Gibson theory claims that affordances are the primary object of perception. We don't see shape, size, color, etc. of objects, but what we see are the actions or the possibilities of actions that can be done on objects. We see places to sit, foods to eat, places to walk. To further show how vision serves action, Prophet et al. In 2003 conducted an experiment where participants had to estimate distances. People were asked to estimate distances to a soccer goal, a tree, or some other object while they were standing in a flat field. Some of the people were wearing a backpack that was about 1/5 of their body weight, while other people were not wearing a backpack. Everything else was the same. The only difference was that one group had a backpack on with weight and the other group did not. Here are the results from that experiment. On the x-axis, we have the actual distance from the target. And on the y-axis, we have the estimated distance that people gave. The red line represents the people wearing the backpack, and the blue line represents the people that were not wearing the backpack. So as you can see, people in both groups underestimated the actual distance to the target consistent with previous distance compression reports, but they did so to different degrees. For instance, when the distance was 10 meters away, people wearing the backpack estimated the distance to be around 9 meters, and people not wearing the backpack estimated the distance to be around 7 meters. These data show that people wearing the backpack had higher estimates in distance than people not wearing the backpack. It may be the case that people felt that the object was further away when they were wearing the backpack, which added additional weight, making the perception of the task harder, or the distance of the object further, because they felt as though it would take more effort. There have been many other accounts of action-specific perception. For example, parkour experts judged walls as shorter, better swimmers judged distance in the pool as shorter, better field goal kickers perceived posts as further apart, and older adults judged distances as further. The overall big idea here is that our perceptual system may have evolved to help us act and navigate in the world. Results suggest that perception is scaled by the perceiver's anticipated ability to act. And this is consistent with action-specific account of perception. So now that we have an understanding of how perception plays a role in our ability to act in the world, we are going to switch gears towards how much detail we actually perceive in our environment when engaging in navigation or some kind of task. So now, let's talk about how much detail we actually perceive in our environment. Look at these two images and see whether you can detect anything changing in these scenes. I'll give you a moment to look at these things. Okay, are you ready? I'll reveal the differences now. So look at the little girl with the black top and shorts. I put a little red circle around her foot. In one version, you can see part of a white sock on her left ankle, and in the other version, you can see part of a black sock. Did you notice that change? It's so subtle. The previous demonstration was an example of change blindness. And change blindness is the inability to detect changes in an object or a scene. Change blindness was first demonstrated in the classic study by Simons and Levin in 1997. The experimenter started a conversation with a random person walking by, and during that interaction, another experimenter walked in between the two carrying a door-like object. During that time, the two experimenters switched places, and the pedestrian failed to notice that change. In fact, about half of the people in this study failed to notice the change. Even more interesting is many were still clueless to the switch when the experimenter directly asked them if they had noticed that they were not the same person they were talking to. Our cognitive processes are amazingly efficient and accurate. However, when we occasionally do make a mistake, the error can often be traced to a smart mistake, such as overusing the strategy of top-down processing. Because we overuse top-down processing, and remember that's our experience in the world, knowledge, expectations, we sometimes demonstrate change blindness. More specifically, we fail to detect a change in an object or a scene. This happens even if you're looking right at the scene. Even though we're exposed to a stimulus, or even interacted with that stimulus, we don't always register the changes in the environment. In order to fully understand what's going on here, we need to understand what attention is, and what allows us to attend and actually perceived objects. And so this will segue us into the first part of our attention lecture. Have you ever tried to pay attention to your attention? Why don't we take a moment to see what that means? First, let's start with looking around your environment and try to notice all of the objects that are around you. Try to notice their size, shape, location, color, distance from you. I'll give you some time to look at these objects and pay attention to them. So as you're doing that, try to also focus on every sound that you hear in your environment. The wind coming in through your window, the street traffic, the hum of your computer, the clicking of your keyboard, the scampering of your cats, people talking as they walk by your house. So as you're keeping all of this visual and auditory information in mind, start to also pay attention to your skin senses. How you feel sitting in your seat, how tight your shoes are, the slight pain in your lower back. Paying simultaneous attention to all of these senses at once is beyond overwhelming. We simply do not have the mental capacity to do this, and even if we did, then interacting with our environment would be very, very difficult. Attention is something that just happens, not something that we often pay attention to. Attention is part of nearly every cognitive task that you do on a daily basis. And so, what is attention exactly? We've all heard phrases like, "Something fluttering caught my attention." "I didn't see you, I was paying attention to the game." "I struggled to pay attention to the lecture." Or, "I don't remember taking that book. I must have not been paying attention." We know that we can pay attention to our attention, but how does our attention escape us? Attention is defined as the mental process of concentrating effort on a stimulus or event or specific location. Attention is the process that allows you to take in a limited amount of information available from your sensory world and your memory. Attention acts as this gatekeeper by allowing you to direct mental effort to what is most important for you at that time, towards your thoughts and stimuli in the environment so that you are able to achieve some kind of goal-directed behavior. And without the ability to attend to important information, it would be nearly impossible to accomplish a task. Just imagine, what if you couldn't attend to anything? Attention has two basic properties that we'll discuss. First, attention is limited. And second, attention is selective. In the next several slides, I'm going to unpack what this specifically means. So in order to demonstrate how attention is a limited resource, I want you to count backwards by threes starting at 669. And while you're doing that, I want you to read the paragraph at the same time. I'll give you a little bit of time to do this. That's hard, isn't it? Did you notice how incredibly difficult doing these two tasks was? Attention is really a limited resource that is used to selectively focus or concentrate on some information while ignoring all other information in the environment. We can test the extent to which people can attend to more than one source of information through divided attention tasks. Here, subjects do more than one task at a time or attend to more than one message at a time. You are likely dividing your attention now by focusing on this lecture and taking notes about the key points in the lecture so that you can do well on your exam. Or, another time that you might try to divide your attention is when you're driving and talking on the phone, or even worse, texting and driving. By dividing your attention to more than one task, your speed and performance on the task suffer. The extent to which your performance suffers depends on the demands of each task and the circumstances of each task. So what has research on divided attention shown us? In one study conducted by Schaefer, skilled typists were asked to recite nursery rhymes aloud while they typed lists of words. While they did these tasks, they measured their typing speed in words per minute. And what they found was that typists could perform both tasks with only a 10% loss in typing speed. This study was initially meant to demonstrate that typing required little attention for highly skilled typists. So what do these results tell us about divided attention tasks? Can we conclude that for skilled typists, typing requires little attention? Divided attention research results are hard to interpret. Are the subjects doing both tasks at the same time, or are they simply switching? We don't know if subjects are doing them at the same time or just switching. Experienced typists often reported that once they had seen a word, they didn't really need to think about that word to type it. That is, the skilled typists reported needing attention only in certain bursts. And just because we can observe their hands typing at a steady rate, it doesn't mean that their attentional resources are needed at a steady rate. In this case, a burst of attention was needed to read the word, and very little attention was needed to type the word. Task switching is closely related to multitasking. If you are deeply engrossed in writing a research project and your roommate keeps bugging you, you are likely to work more slowly and make more errors during the transitions. So now that you know that divided attention requires that people pay equal amounts of attention to two or more tasks or sources of information, what do you think selective attention is? So I know it says it right here, but selective attention requires you to pay attention to specific kinds of information while ignoring other ongoing information. So we're pretty good at ignoring stimuli we are not going to pay attention to. For example, if you are focused on this lecture, you may not pay attention to all of the sounds happening in your environment. It may not be ideal to completely ignore everything. So through selective attention, we have developed the ability to focus in on specific stimulus that provides information about our current goal state. That is, in this case, taking notes while listening to this lecture. Selective attention can be studied by using selective attention tasks. In these tasks, participants respond to one source of information, which can be visual or auditory, while also ignoring another source that occurs at the same time. A classic example of this is the dichotic listening task, and this is a common task used to study selective attention. So in the lab, dichotic listening is studied by asking people to wear headphones, and one message will be presented to the left ear, and a different message will be presented to the right ear. Usually, the research participants are asked to shadow the message in one of the ears. More specifically, they have to listen to that message and repeat it after the speaker. If the listener makes mistakes in shadowing, then the researcher knows that the listener is not paying appropriate attention to that specific message. In 1953, Cherry conducted a dichotic listening experiment to investigate two important issues. What are the differences between two concurrent auditory messages used by listeners to select one and ignore the other? And what information do listeners typically extract from the message that they are not attending to? In this classic research study, people were asked to listen to two different stimuli in each ear. For example, in one ear they heard the meaning of life, ... and in the other ear they heard the yellow dog chased, ... The experimenter told the participant to only focus on what they heard in the right ear. As they did this task, they were asked to repeat back the words that they heard, and this is referred to as shadowing. Overall, people were pretty good at this task. That is, they were pretty good at repeating back what they had heard in the attended ear. However, people noticed very little about the unattended second message. For example, people didn't even notice that the second message was sometimes switched from English words to German words. People did notice, however, when the voice of the unattended message was switched from male to female. So what could these results suggest? They suggest that top-down processes, that is, our expectations and knowledge about the world, play a role in selective auditory attention. We are told to repeat back words that we heard in a specific ear, so we then selectively attend to that ear and are able to repeat those words back, but we're not able to repeat the unattended message back. In another dichotic listening experiment, Moray really wanted to assess what circumstances could lead people attending to the message in the unattended ear. In this experiment, people had to attend to one message in the right ear, which was a full sentence. In the left ear, people heard a short list of words, such as dog, apple, cat, chair. This list was repeated in the unattended ear 35 times. However, since people were asked to pay attention to the right ear, they were unable to report any of the words that were repeated in the left ear. Even when they were presented with a list with some of the words on it, they were not able to identify those words. People focused their attention so much on the right ear that the information in the left ear could not be attended to. So what does this tell us? This is starting to tell us that, in general, people can only process one message at a time, and that message is guided through our expectations, that is, being told to attend to one ear, so that we selectively process that information. Research from dichotic listening experiments led Broadbent to propose an early filter theory in 1958 to explore how we focus on some information, but not everything. Overall, this early selection model of attention posits that stimuli are filtered, that is, that they're selected to be attended to, at an early stage during processing. So in our previous example, the experimenter told the person to listen to what is coming into their right ear. A filter can be regarded as the selector of relevant information based on basic features such as color, pitch, direction of stimuli, size, etc. So let's walk through this filter model. The stimuli must enter into our sensory memory, or sensory store, that is our eyes, ears, nose, in order to process that information. After the information is received by the receptors, the information is sent to the selective filter. The filter takes information and identifies the physical properties such as pitch, loudness, color. The filter takes in all of the information, but only allows the attended information to be sent to the detector, which processes information from the attended message to determine higher level information, such as the overall meaning of that message. So this would be when you're repeating back the sentence that you're supposed to shadow. The detector processes everything that made it there this far. The information eventually reaches our awareness and enters our memory. So what actually gets through to the filter? Information is only analyzed for its physical characteristics, so only stimuli that are very distinct physically will make it to the next stage. Remember the Moray experiment? This was one test of the early filter theory. They conducted another study with the hypothesis that if the message is the same physically, it won't be analyzed further. Remember that people were told to attend to the sentence presented in the right ear. Instead of a list of random words presented in the left ear, the participant heard their name in the unattended ear. When asked if they heard anything in the unattended ear, 33% of those people noticed. This is referred to as the cocktail party effect, which is the ability to focus on just one stimulus in a very noisy environment. For example, have you ever attended a social gathering when you are surrounded by many simultaneous conversations? And even if you're paying close attention to one of those conversations, you may notice if your name is mentioned in a nearby conversation. This is one of the experiments conducted around the 1960s that provided evidence against this early filter model. Another study conducted by Ann Treisman in 1960 also provided evidence against the early filter model. In this experiment, the messages were intentionally switched in the attended and unattended ear. In this experiment, people were told to listen to the message in the right ear, which started as, "While Bill was walking through the forest," but then switched to, "A bank can lend you money." In the unattended ear, the message began with, "If you want to buy a car," then switched to, "A tree fell across his path." The coherent messages that were presented but split across the two ears were, "While Bill was walking through the forest, a tree fell across his path," and "A bank can lend you money if you want to buy a car." If the early filter model is correct, then the person should report what was heard in the attended ear. So what they should report is, "While Bill was talking through the forest, a bank can lend you money." However, people said the coherent statement, "While Bill was walking through the forest, a tall tree fell across his path." They didn't even notice that they had switched to listening to the other ear. In her experiments, Treisman demonstrated that participants were still able to identify the contents of an unattended message, indicating that they were able to process the meaning of both the attended and unattended message. So this is that support for evidence against the early filter theory. So overall, evidence against the early filter model shows that we don't just process information based on physical characteristics. We also process information based on its meaning and the context. From this research, Treisman developed a new model called the attenuation model of attention. In this model, selection occurs in two stages. First, once the stimuli reach the sensory memory, information is sent to the attenuator, which processes information based on the physical characteristics, as well as the language and meaning. The attenuator allows information to move to the next stage. The attended message is emphasized, so it's sent at full strength, while the unattended message is de-emphasized, it's weakened. Next, the information reaches the dictionary unit, which consists of a list of words. Each word has a specific threshold required for being activated. So remember that a threshold refers to the smallest signal strength that is just barely detectable. So a word with a small threshold requires a weak signal to be activated. And this would refer to words that are very common to us, such as our name. Another proposed model is the late filter model. In 1973, McCabe presented an attended message in the right ear, "They throw stones at the bank," and a single unattended word in the left ear that was either money or river. The attended message is ambiguous. That is, "they throw stones at the bank" could be associated with either money or river, because bank is associated with a riverbank or bank in terms of money. If they heard river, they selected "they threw stones toward the side of the river." If they heard money, they selected "they threw stones at the Savings and Loan Association." So what this shows is that meaning matters in terms of what you attend to. The late selection theory suggests that most of the incoming information is processed to the level of meaning. This theory argues that information is selected after processing for meaning, as opposed to during the early stages of processing. So which theory is the right one? Early theory, the attenuation theory, or the late theory? Each of these theories explain the data in different ways, and they all provide insights into how information is selected and processed. So by synthesizing the evidence from these theories, researchers have been able to develop a theory that integrates aspects from each of these. The movable filter theory is a model that takes parts of each of the models that we've discussed. This is an attentional model where the filter can be chosen to be either early or late in the processing stream, depending on the needs and resources. So depending on the task or your goal-directed behavior. In this model, unattended stimulus are analyzed for physical characteristics. Then we choose to allocate our attention to some material or allocate our attention mostly to the material, and switch periodically to the other material. If you need to detect something based on physical properties, then the filter occurs early. But if you need to detect something based on meaning, then the filter will occur later. The movable filter theory takes into account the language, meaning, and physical characteristics, all of which are similar to the previous theories that we've discussed. Johnston and Hines conducted an experiment in 1978 that provided evidence for the movable filter theory. In this experiment, participants had to listen to two different word lists over headphones. As they listened to the lists, they had to shadow the information based on physical characteristics or based on meaning. For example, whenever you hear a female voice, you will shadow that word. Or, whenever you hear a word related to nature, you'll shadow that word. While they were listening to both streams of information, participants were tasked with watching a screen, and whenever the light appeared on that screen, they were required to press a button. Results demonstrated that participants took longer to react to the light when they had to shadow for meaning, compared to when they had to shadow for physical properties. This suggests that filtering information based on either physical or semantic properties occurs, but for semantics, the meaning takes more effort. While they can filter information based on either physical or semantic characteristics, shadowing on the semantic level interfered more than shadowing on the physical level with the secondary task. This suggests that we can differentially allocate attentional resources based on how effortful something is. Overall, the takeaway from this research shows that all stimuli are evaluated for physical characteristics and that further processing requires more resources. In our next lecture, we'll continue our discussion on attention and elaborate more on different modes of attention.